An air hose has a cone on its end, and when air is rushing outward, a hollow plastic ball is suspended. How does the Bernoulli equation explain this? So what I'm talking about is drawn here, and maybe what's not quite described in words there is the ball is actually kind of hanging out of the bottom of this cone. So when there's no air rushing, it would just fall down. In fact, you might wonder, wait a minute, if there's air rushing, shouldn't that just push the ball out faster? And yet, in fact, this can be done. And that's not what happens. The ball actually gets kind of looks like it gets sucked in, even though the air is rushing out past it. Well, how can that be explained by the Bernoulli equation? Now, one issue I often find with these kinds of demonstrations using air is that air is not really an incompressible fluid, and in that sense, expecting its density to be constant is not correct. And yet, there are a wide range of demonstrations of the Bernoulli equation involving air. So apparently the Bernoulli equation works well enough to explain these things. And maybe to explain this one, I have the Bernoulli equations moved up to the top of the board from the last example. Let me redraw kind of the picture here of this air hose with a cone attached to it. Oops, hang on. Let me make that more, maybe closer to a 45-degree angle there. Okay, that may be a little bit exaggerated, I suppose. And then here's the ball. I think the picture on the slide is way better than this. The ball is usually kind of almost the width of the cone at some point there. But nevertheless, this will work. So one way to think about this is to say, okay, let's say here's a flow line. Okay, and this flow line kind of goes out and around the ball. And if you kind of compare like a point right here, let's label that point 1 to maybe some point 2 over here along the flow line. And at that point, the air at some distance, the air is basically going to be stationary. And we can actually say, or we can argue, that that stationary point for the air is going to have the same conditions as some stationary air that's right underneath the ball right here. So actually, what I'm trying to argue is I can make that or label that with the point 2 as well. For the point 1, we have a very large V1 right there. In other words, I'm just going to write over here, V1 is big. And so what does that mean? If V1 is large, and in particular V2 is actually, in fact I'll write that down here, V2 is basically equal to 0. Well, V1 is big. If this term is big, something else must be smaller. And I'm actually, in looking at this, I'm not going to think so much about these height terms. I mean, they're there, but the height change here might be small enough that I'm not going to worry about them. So in reality, there is some height change, but we don't have any numbers for this. I'm just going to claim I can get rid of those, and we're just going to look at pressure versus speed. So if V1 is big, that means P1 is going to be small. So that's what I'll write here. Pressure P1 is small, and V2 being equal to 0 is going to imply that P2, I'm just going to say, is large, but really it's as large as it can be, because when the air is still and not moving, that's the condition for the pressure being as big as possible. So for this ball, in that sense, maybe if I redraw the ball down here, it's experiencing a pressure P2 underneath it, and then the pressure P1 is kind of being applied to it sort of on two ends, maybe to the right and the left, but basically at the top of the ball. So if P2 is a much larger pressure than P1, that suggests a net force that is upward. Although maybe I should say that this is the net pressure force. So I'm just gonna put pressure here, because there's also, like, really, if I say what's the net force on the ball and it's just sitting there and not accelerating, the answer should be 0. And that's because there's also a weight force. In that sense, if I were to draw this as a free body diagram, maybe thinking about this a little bit more deeply than I feel like I need to, is to say that that overall net pressure force is really countering the force of gravity. And if they balance, that means the ball will stay there. All right, let's look and see what the slide does. The slide brings in V1, P1, V2, P2 at the bottom, and it says the pressures and flow speeds labeled can be compared with the Bernoulli equation. Since airspeed V1 is much faster, the pressure P1 is much lower than pressure P2.